Okay, we might as well get started then. Hi everyone, my name is Michael Hines. I'm a graduate student in the Department of Applied Math here at Waterloo. And today I'm going to be giving a summary of a paper by Graves et al. And it's speech recognition with deep recurrent networks. And this is a work that was presented to the International Conference of Acoustics, Speech, and Signal Processing in 2013. And it reports some very interesting results on a classic data set. So as a bit of an overview, first we'll start with just a problem description of exactly what they're trying to do and their contributions. And then we'll talk about the networks they actually use, starting from their input, how they pre-process the data, and then talk about the models they've used, as well as the two different output layers they had for making predictions. And then we'll talk about the experiments they used, or experiments they did on this data set, the methods they had to optimize. And then we'll have a bit of a discussion about the statistical validity of what they presented. So to start with the very basics, we're looking at phoneme recognition. And a phoneme is the smallest meaningful contrastive sound unit. So in this table, for instance, you'll see a lot of sounds in here like beat, or bit, or bet. And each of these are the individual small pronunciations or small sound units that you can make. Now, most languages, including English, have about 40 phonemes, or 40 unique sounds. And this table is actually from the corpus that they've considered in this paper. So what does identification actually mean? It means that given this waveform, this recorded audio waveform, which is just going to be human speech, please call Stella, you want to actually identify the small bits and parts of this waveform that correspond to individual phonemes, which in this case would be a P and L, the sound of all, the k sound, that stop. And then you want to actually segment them. So you want to take this waveform right here and turn it into the actual individual sound units and the time at which they occur. So the broad overview of what we want to do and what Graves et al. Presented is this following network here. They take the audio waveform, they input it and convert it into a sequence for a recurrence neural network. They supply it and they process it through this network, and they get the output phonemes. So here, phi with whatever subscript corresponds to some sequential phoneme, and t with the subscript corresponds to the time at which it occurred in the waveform. So the main contributions of this paper were some studies done with this TIMIT corpus. This is the Texas Instruments MIT corpus. And it's a very standard data set in the field of speech and phoneme recognition. And what it is 6,300 waveforms, which are made from 630 American speakers. And the historical results have generally been halted about 80% correct recognition. So in the past few years, there's actually been a fair bit of progress by neural networks and Boltzmann machines. And just the year previously, the best result reported was about 80% correct recognition. Now, what Graves et al. Did, though, was they presented, in this case, deep short-term or long short-term memory networks. And they also used something which is a bidirectional network. And they've basically extended their previous work, or at least previous work by Graves, in taking bidirectional long short-term memory networks and then converting them into deep bidirectional long short-term memory networks. And so the important thing is that with increasing numbers of layers, they actually get to 96% error rate, which is very, very good. And the best rate that they actually achieve is 17.5. And so this is a previous result by actually one of the authors of this paper, Mohammed, but it's been beaten fairly significantly in this current formulation. OK. Any questions at this point? Great. So we'll just talk here about, first, the input to the network. How do you actually take the audio waveform and convert it into something which is useful for feature extraction? So the key thing is the Fourier transform. And we'll give a brief overview of the transform just to jog everyone's memories back. So if you have a real periodic signal, you can transform it into the frequency domain with the following transform. And this is, of course, theoretically important, but in practice, we're talking about a discrete Fourier transform, which is computing at a finite discrete number of frequencies the components, or the spectral coefficients, if you will. And so what this actually looks like, though, is that you take some waveform here in the time domain, you process it, and you get out a spectrum. So each of these bars here corresponds to the amplitude or magnitude of the spectral coefficient at the frequency omega. Now, when you do this in the following way with windows, what you're actually computing is a series of windowed DFTs. What you get is, within this window of duration tau, a spectrum of all the frequencies that occur in this part of the waveform. If you slide over to the next window, you're going to get another spectrum, which is going to be different because you've taken a different set of samples, and you're going to get a different spectrum because the spectra are unique. And so what you get in the end for a waveform is now a set of spectra, which when you stack them all together, actually produces now a two-dimensional plot. So from the previous spectra you saw, that would be one vertical line. The next spectra with the next window would be the next vertical line. And when you stack them like this, you're going to get what's called a spectrogram. So along the x-axis, you have elapsed time of when the waveform started. And along the y-axis, you have the frequencies that are important. So you can actually really see what's happening in this waveform. This actually happens to correspond to the first bar of Hey Jude. So you can see the first frequency going down to the Hey Jude, dun 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 dun. And the bottom is like the fundamental frequency. But then there's still resonances which appear on the higher order terms. And so if you had a really nice guitar doing the same bar, you'd see many, many frequencies going all the way up. But I don't have the same sort of resonance as a very well-made guitar. And so why is this important, though, for speech recognition? Well, this is actually from O'Shaughnessy. It's a paper about frequency resolution and frequency views of phoneme recognition. And so if you look at the stops, or the sounds in English in which you actually stop making sound, like a P or a D, when you fully close your mouth, you can see there's actually a very interesting spectral envelope. So for instance, this ada sound, you can see how this frequency is really dying away, but the higher frequencies are gaining in strength just before you actually hit the D sound. And so really, any phoneme you make really can be characterized as this parametric waveform in both the time and frequency, I don't want to say time and frequency domains, but a long time in the frequency domain. And so not only can you look at the actual spectrogram, you can also look at its derivatives in time. And so the way you compute this is, unfortunately, numerically, so there's still plenty of error. But you take each vertical slice across frequencies, and then you compute differences going along horizontal slices, which will give you your time derivatives. And so you can see that in this plot here, there are small differences or small changes in the derivative that actually pop up that you can't quite see as well in this plot here. But of course, when you have changes in frequencies, they do show up very strongly. And the red part is just to do thresholding. I've cut out values above a certain amplitude in the right plot.
So is the phase thrown away?
So, okay, good question. So when you do a Fourier transform, you're computing two things, really. You're computing both the amplitude and the phase that correspond to that frequency. But when you're looking at the coefficient in terms of its magnitude, you may only want the amplitude, or you may only want the actual power of the waveform, which is just the squared amplitude at that point. So you really are throwing it away. If you wanted to go back, though, like let's say you actually had all of your coefficients of the waveform, and you wanted to go back into the time domain, you would actually still have to know the phase, because even if you started all the individual frequencies at the exact same time, it won't sound at all like the real waveform, because each of the frequencies have been shifted somewhat. So for synthesis, it'll be more important. Now, there's one little thing which I want to mention here, which is very important in frequency domain processing, and it's the uncertainty principle. So people from physics will probably think of this first as being position versus momentum, but the proofs for why that comes about are mainly because of the Fourier transform and transforming between the two frames. So if you take, for instance, a very small window, which would correspond to taking just a small segment of a longer waveform, you're going to have very few samples to compute your frequencies. However, you're going to have great temporal resolution. So you can see here that these frequencies have been really blended. There's a very large spread vertically, but very little spread horizontally. So you know exactly when the frequency changed in time. But you don't know exactly which frequency it was. It's somewhere around 20 hertz. You don't quite know what. And as you increase the sample size, well, the vertical broadening is changing. It's decreasing. But now suddenly you've got more spread horizontally in the time axis. And you can keep going to larger and larger window sizes until suddenly you know exactly which frequency, but you have no idea when it started or when it ended. So there's no free lunch in doing a windowed DFT, because you probably want this, but you may get this. So something to keep in mind when you process any sort of audio input. So as for what Graves et al. Actually did, they have a series of waveforms for what has been recorded from all the speakers in the TIMIT data set. And each waveform has been computed into, or has been, for each waveform, a window DFT has been computed with a 10 millisecond window duration, which corresponds to 80 samples for the sampling frequency at which the waveforms were recorded. And so this corresponds to 40 unique coefficients. So in that previous spectrogram we had on the vertical axis, you only actually have 40 unique numbers. And they, of course, have also added in both the second and first time derivatives. So your complete input vector is actually C1, so the amplitude at frequency 1, its derivative, its second derivative, the amplitude at frequency 2, and then its derivative and second derivative, and so on. And the other thing they do, which is a pre-processing technique, is each of these samples across the entire data set were all shifted to have zero mean and unit variance. And we can talk about that a little bit later, but it's actually a questionable point of what exactly that would mean when you look at the physical properties of shifting the spectra and whether or not that's actually really what you want to do. OK. Any questions at this point? So we'll move on then to the network models. So this is the point. Oh, sorry.
Are we going to get back to this point that you just mentioned, that shifting, what it would mean physically?
Yeah, we can talk about it a little bit later in the discussion. Because it's a question of how you want to pre-process your data. And basically, I can show you some examples that I've taken where you can high pass or low pass filter a signal. And it's very interesting to see what happens, because you can understand a signal perfectly when you low pass all the low, when you high pass filter it and take out all the low frequencies. Those don't really mean anything in terms of phonemes. All the phonemes we produce are above 1,000 hertz. So do you really care about the coefficients? If you only have 40, does it really matter what the bottom 20 are? So it's kind of questionable. How much do you really care about the low coefficients? And how much do you want to spend time training the network to recognize them when they don't really matter in the first place? But we can come back to that. So about the so the MEL coefficients are just another way of representing the amplitude. So if you just compute your DFT, you're going to get what we would call, I guess, a linear representation. Whereas when you look at the way that humans actually process sound, we have a logarithmic interpretation of it. So high frequencies mean less to us in terms of the differences. If I sing a note to you at 4,000 hertz, that will sound almost exactly the same as a note at 5,000 hertz. Whereas 400 hertz versus 500 hertz to you sounds like a huge difference. So the MEL frequency really doesn't change what you're actually processing. It just changes the relative magnitude of coefficients. Yeah, I guess the idea is they want to model what a human could hear in a way. So don't have the network learn from things that a human couldn't learn from. Also questionable, because you can get a bit more resolution in a sense from the Fourier with a linear scale, but. OK, so we'll just go over recurrent neural networks very, very briefly. And starting with just a single layer recurrent neural network, we're still talking about a sequence of vectors that we want to convert into some hidden sequence of vectors, and then to our output vector. Now, the normal transformation that we're going to care about is a parameter matrix, which is going to be an affine transformation, and then this also offset bias term here. And we compute h from the standard equations, which are very similar, some nonlinear, generally sigmoidal or hyperbolic tangent function. And we have to just keep in mind that when we're talking about the first input to the sequence, there is no such thing as h naught. It's just h1. So using the recurrence relation, though, we can easily compute the output vectors. But when you generalize this, of course, to many layers, you suddenly have a very general recurrence formula. So to go from a hidden vector at one time step to, and one layer at one time step to the next layer at the same time step, you're going to bring in information from still the current, or I guess previous hidden layer, but also the previous hidden layer in time and the current state at that layer as well. And so it's good, I think, to remember that we're looking at some dimension here of output vector, and then the transformation that's going to bring us from the previous layer to the new layer is not going to be a square matrix in general. However, the recurrence terms from the last time step will have to be a square matrix. So that process of having the general sigmoidal or hyperbolic tangent function is a bit more general with the long short-term memory. And this is an architecture which has a little bit more in it because it's a composite function. So each layer has an associated cell state vector. And this actually is updated for each time step. So there's not just a hidden state, there's also a cell state, if you will. And so you now actually have a hidden vector which depends on the previous state, the current input in the sequence, and then also the previous hidden vector. So you suddenly have more inputs to each layer. However, it's very familiar in the sense that we're just going to be doing many Hadamard products and many sigmoidal flattening functions. So here, the dot here is the Hadamard or element-wise product of two vectors. And so they're going to input the current state, but they also take inputs of the current input, the previous hidden state, and as well in here they also use the cell state again. So there's a lot of there's a bit of redundancy, I find, in this first term. And as for what the cell state actually is, well, you have a forget gate and also an input gate. And the motivation for this forget gate is if each of the elements of these vectors are in the range of 0 to 1, they're essentially like probabilities. And so this forget gate in the Hadamard product here can be seen as a yes or no, or a bit of a thresholding function on whether or not you should remember the previous cell state. So if ft is essentially all 0, it means forget this state. Whereas if ft is almost all 1, it means use the previous state because it's still relevant. And then, of course, they throw in just more parameters. So the full equations end up getting a little bit hairy, but there are a few simplifications to this. The first one, which is the most important, is that each of these W matrices is actually, so you have to optimize them all, but the key thing is that they are diagonal. So in this particular long, short-term memory architecture, you don't have to worry so much about solving these huge parameter matrices. They're all just diagonal scaling matrices.
Did they consider using, instead of sigmoidal, like the rectified linear function? Would those apply here?
They don't mention using the rectified linear. They do a few experiments with a hyperbolic tangent function, but no, they don't really talk so much about the architecture. There are previous papers that discuss its use in other problems, but it's a very short paper. They just give the results.
So what is diagonal? Why W is diagonal?
I assume the real reason it's diagonal is just because you have so many parameters now that when you make it diagonal, you only have, for an n by n matrix, you only have n terms now to worry about. So essentially, you're only having to store vectors instead of matrices. In terms of whether or not it's better, it probably is better in the sense that you have less overfitting and less generalization error, but they don't really elaborate on it, I'm afraid.
We are restricting the type of transformation that we can have, right?
Mm-hmm.
So we restrict it to just scaling here?
In the input and forget gates, yes. So when you actually take the output vectors, those aren't, in general, diagonal. So the diagonal matrices would correspond to these input and forget vector gates, whereas when you actually compute, I believe, these hidden vector layers, they're not extremely clear on this in the paper, but it seems to me that they don't restrict this to be diagonal. So I think that just these parameter matrices here are diagonal. Any other questions? Okay. So the other thing that they add to the architecture is bidirectionality. So essentially what you're doing now is instead of just one, you're computing 2 hidden vectors for each layer. And the way that they think of this is that you have some forward hidden vector, which is just a conventional recursion. So this is if you just add a forward arrow on the previous vectors, that would be the same hidden vector. But then they have a second hidden vector that they compute, which actually uses the reverse sequence. So they call it the backward vector, and it is computed still through a recursive relation, but from x big T all the way down to x1. So the only real difference here is if you look at the indexing of T, it's no longer T minus 1, it's T plus 1. So again, just seeing it as reversing your sequence and computing a forward hidden vector on that. And the motivation for this is that in a lot of sentence modeling, or if you want to do word prediction, the word at the beginning of the sentence could actually matter very much or could relate very much to the word at the end of the sentence. They don't elaborate on why this is so much better than unidirectional, and there's only one test, so we can talk about that. But previous work they have done has shown this has been very, very good with non-deep, just one layer networks. So even if you have these 2 vectors, your final output vector is now just going to be an affine combination of these 2. So there's no real difference in the mechanics of what you're doing. You still just compute all your derivatives with respect to ht forward and ht backward, and then you can still train this network. And yeah, essentially what you're doing is you're, in each step, combining 2 networks on different sequences, but 2 very related sequences. OK, any questions about bidirectionality?
How much improvement was there between just a regular forward kind of causal one and having both of them? Was there a dramatic improvement?
No. In this paper, I would say probably, possibly negligible. It depends on really how significant the differences are in these numbers, because the tests weren't done with many measurements.
Okay.
So we'll talk about that. That's my reaction too. So there's a previous paper, though, I should mention this, that it was Graves and Schmidhuber that did this before. And they were looking at non-deep networks, but they did actually see quite an interesting improvement. So I can actually pull up the paper and just show you the figures afterwards.
I know I've seen it a couple of times before where they use bidirectionality. I think Hinton uses it in some paper. I guess the idea is that context thing.
Yeah. You care about words in front and behind.
Yeah.
So, I mean, you have to wonder if it's worth using a full actual backward network, or just including recursive matrices that go forward a little bit too.
Yeah.
But it has shown really good improvement in the past. OK, so we'll just talk about the 2 output layers that they've used here, because they're 2 distinct ones. And I'm not going to harp too much on the second one. But basically, the first one they considered was this connectionist temporal classification. But in truth, it's really just a softmax. So you have a set of phonemes in the data set, which is 62 phonemes. But you also have a null symbol, because when you listen to the full waveform, you'll only hear words every half second. But there's still a 10 millisecond window that you've been sampling. So you have many, many samples and very few phonemes. So you still have to have an output null phoneme. And then the second model, which is more complicated, they call an RNN transducer. And so basically what this is, though, is a whole other layer. It's essentially constructing an output network which takes the hidden forwards and backwards vectors of the last layer, and they feed that into another recurrent neural network. So the equations they give in the paper really just show it as being another layer to the network. But the way they train it does modify slightly the actual outcome they get. So it's an interesting idea. OK, and so we'll just talk very briefly about the connectionist temporal classification, or just the softmax. You compute your YT, and you apply the general softmax probability to it. In this case here, they just report that at each time step, they don't have to worry about any previous dependencies on any other time steps. They do a little bit more magic behind this because you have so many actual parts to your sequence, right? You know, this T, the big T, is actually very, very big. But they shrink it a little bit because they only care about comparing between phonemes that actually exist in the segmented ground truth waveform. But you know, you can forget about that. If you want to actually do this at home, just use a softmax. Now, the second one, again, is a little bit more complicated, but it will be the same song, second verse as before. You just compute a new layer here, or a new hidden layer vector, and it combines the two vectors that you use as the input now, which were the output of the previous network, and then you have to compute as well the hidden vector, but then you also make this new hidden vector in the second network, which combines LT and then PT. So there's a little bit of magic happening here, which they don't elaborate on too much. And whether or not it really helps, again, we'll talk about, because it doesn't show a huge improvement when you train them in the same way. But yeah, just bear in mind that this HT T prime actually has dependencies on all input vector time steps. So when you actually compute now your softmax of the final network output, you don't just have a single sequence to worry about. You actually have the phoneme dependent on T and T prime. So that's all phoneme steps, or all sequence steps in one network, and all sequence steps in the next network. So in general, this is big T squared. There are a lot of terms you have to take into account here, which is why in practice they have to use a beam search decoder to actually compute this. So it adds quite a bit of complexity in practice to use this other output function.
So just to summarize, what's the input to the RNN transducer and what's the output?
So the input to the RNN transducer is the output of the CTC network, or the output of just a softmax layer. So it really is just a continuation. It's like taking another layer on the previous network that we'd already been working with. And the output is the same thing. The output is just going to be the probability of one of these phonemes, phi k, given the time step of the sequence from the CTC layer and the sequence in this new transducer layer. So, which is why, again, you have this.
So what's the intuition behind having this?
Okay, so the intuition that they write is that the first layer network is going to just be about detecting an acoustic phoneme model. And the second one is supposed to be incorporating language recognition. But, I mean, when you look at these equations, I don't see that personally. The way it's just some general hidden vector. So I actually don't think there's any real intuition based on the way they've trained this. But, I mean, maybe I'm misunderstanding it. Any, yeah, if anyone has any intuition about that too, just let me know, because it doesn't seem to correlate with what they've said to the equations they've written. OK, now for the actual experiments, and what did they really put in these neural networks in the very center here? So the objective function they used was always maximum log likelihood of the known phoneme segmentations. And they had to determine the parameters in each of these matrices. But they used stochastic gradient descent. And in all cases, they used a fixed learning rate and also a momentum term. And the initialization of each of these parameters was just drawn uniformly. So nothing terribly fancy, very standard. But because of the way that you're comparing across models, you're not going to have the same initializations between all these experiments. So there are very different numbers of parameters between the experiments, as we'll see. So they split up the TIMIC corpus into two sets. One set, which is the training set of 462 speakers, and then a second set, which was their testing or development set, which had 50 speakers. And the way they actually trained their networks was they first ran SGD on the training set until you had maximum log likelihood on the testing set. So at each iteration of your optimization procedure, you have to print out the max log likelihood on the other set as well. And then once you've gotten to a point of, if I maximize that, you then rerun SGD with noise added. So the regularization in this case has just been a noise addition. And then, oh, and I should mention too that the noise is added not for every time step, but for each individual waveform instance. And so then once they ran the final, after the pre-training stage, they did the final training, and they stopped it once the phoneme error rate stopped decreasing on this testing set of 50 speakers. So a few stages. The first one is just to get you in the regime of a good solution. And the second stage is to add in noise and improve the generalization error. So in terms of what they did, the main experiment that they're showing here is increasing the depth of the network and then looking at the phoneme error rate. So you want as low a phoneme error rate as possible. And they've conducted experiments with 1, 2, 3, and 5 layers, each layer having 250 hidden units, which is why this is named CTC 1 layer, 2 layer, 3 layer, 5 layer, and then 250H. And so you can see that you increase the number of parameters as well, but you also are decreasing monotonically the phoneme error rate. So as you increase the depth, you definitely do a lot better on this data set. And the final two numbers, they're very, very close, but it still decreases monotonically. However, I have to wonder why they left out the 4th layer and what the actual error range is, because it's a stochastic optimization algorithm, and there could be a fair bit of wiggle room in these two numbers. Now, the other experiment they report very briefly is by increasing the number of parameters within a fixed layer size. So there's only one experiment done, though, and it's with a single layer. And they increased the number of parameters from 0.8 million to 3.8 million. So quite a large drop. And you have to remember that this 3.8 corresponds to the 3.8 of the 3-layer network. So as many parameters as 3 layers, but you can see that the error rate is significantly lower for having 3 layers versus 1 layer. And that's something that people take as a general expected phenomenon.
So what parameters did they change? So like instead of just having uniformly, like what was uniform and that then became segmented? Like what did they change?
So in this case here, they have 1 layer, but they increase the number of hidden units. So if you were to draw out the neural network as a series of LSTM cells,
so
you're going to have more cells. Yeah, so it's getting broader,
makes sense.
but not deeper. And so this is kind of the conventional wisdom that if you make it deeper, it does better. However, you have to remember this is just n equals 1. They didn't try this with n equals 2, 3, 4, 5. Does this really still apply in general? Does it actually help when you go to n equals 3? So still something that you have to wonder. And then for this other experiment here, which is the unidirectional case versus bidirectional. So this is kind of the key questions that actually someone had earlier, which is you can take a 3-layer bidirectional, just general network with tanh activations, just regular MLP essentially. You can take a 3-layer unidirectional LSTM and then a 3-layer bidirectional LSTM. And since they all have about the same number of parameters, you can compare the error rates they get here. But even though these two numbers are quite similar, I still wonder if you had done 20 experiments and then you had computed what is the actual variance in these numbers, is this really a significant difference? And it may be, it may not be. But it's also very dependent as well on the way you've optimized it. I mean, if you change the optimization algorithm, maybe it would take more epochs to actually train this network. So there's a bit of a questionable comparison here. But they seem to show that it does actually improve the recognition rate. OK, and then so the final comparison is between this transducer model versus just a simple softmax layer. And so the transducer model was trained as before. You just initialize all the parameter matrices or parameter vectors for the diagonal cases, and you train from there. You go to the same procedure as before, where once your maximum log likelihood stops decreasing in your pre-training phase, you then go to your full training phase with Gaussian noise. But they also have a different one, which is a pre-trained, and they call it pre-trans 3L250H. And this is actually a network which has been started from an already trained CTC softmax output. So they've already trained everything separately. And then they retrain the network starting from that point. So this is a totally different ball game here, because they've started it from very different initial properties. And so if you look at the phoneme error rate here, well, there's certainly a bit of a decrease going down, but 18.6 and 18.3 between this CTC network and this transducer, I mean, it's a very, very small difference. And within stochastic optimization error, I'm sure that's actually negligible. As for the pre-trained transducer, it actually achieves the best phoneme error rate. It's the lowest one that's actually ever been reported in literature. But it's still, well, it's a very good result. I still have to question exactly how fair this is, because there's more parameters and it's trained in a very different way. It's likely you can improve all these numbers by training them in this analogous fashion. OK, and so yeah, this is just to reiterate this. The authors state in section 4 that the experiments were run only once, so the variance due to random weight initialization and weight noise is unknown, which is kind of like the first thing that you'd have to ask as a reviewer. Can you repeat the experiments 10 times and report the standard deviations of all your measurements? So the key thing to note here is that if you don't have any uncertainty bounds, you can't make certain conclusions. So just to review the previous numbers, it's hard to say if something like this, 18.6, is any different than 18.4, because if you look at these uncertainty bounds, they really are the same measurement. So just to kind of recap here, you can decrease the phoneme error rate on these increasing depth experiments, but they really do level off. But there's no 4L here. Why isn't there a 4L? And then why don't you add some error bars here to know if these are actually different? So depth helps, but only to a certain point. And then the same thing here is that, well, the bidirectional layer may be better, but it's hard to say how much better it really is without further statistical analysis of it. And the same thing with the transducer. These numbers are just way too close for us to actually draw conclusions. So I would say that the only conclusion that we can say with any certainty is really that the network that they've devised, this bidirectional LSTM, has certainly done very, very well, and the way they've trained it is very good. But to say that bidirectional is better than unidirectional, that's debatable. To say that depth helps, yes, that probably does help. Anthony?
So do you think they simply could have just included running the experiment 10 times with different initial guesses, and that would have been enough, really?
Well,
and different Gaussian noise or whatever?
Even if you ran it with different initial guesses and you still use a stochastic sampling, as long as you use the same stochastic sampling, then you could run it with different guesses. You could run it from the same guess with different stochastic permutations. That would still give you a different result, too.
You could even do both different.
Yeah, exactly. Like, there's so many ways you can actually get uncertainty measurements that, it's certainly an interesting idea. I just wish that there had been a little bit more statistical analysis done to be able to say concretely that, this bidirectional network is really a lot better than unidirectional, because we can't really say with any certainty if that's the case. OK. So yeah, thank you very much. And if you'd like, we can talk more about the frequency processing, but I'm afraid that, yeah, we still have time. So any questions, actually, before? No? No?
What's the main difference between their structure and the previous structure created by Muhammad?
The previous structure by Muhammad?
Yeah.
Oh, to be honest, I don't believe that Muhammad was using LSTM at all. They weren't using boltzmann machines, but they were using another type of deep network. I'm afraid I can't remember off the top of my head, but it wasn't an LSTM architecture.
Using a deep belief network?
That sounds familiar.
Yeah, I think that might be what they were using.
Mm-hmm. So there are two, I guess, previous papers. One is LSTM that Graves worked on. And then the other one is by Muhammad, which is the deep belief. And this is kind of that applying LSTM with a deep network to the same problem. But the motivation is good, perhaps, but you're just throwing so many parameters into a model, and you really want to cut down the parameters whenever you can. So, which is kind of why actually I just wanted to mention that. So when you look at a low pass versus a high pass filter on an audio waveform, so this is just a recorded audio sample. It actually comes from the Timmett data set. And if you filter this such that you let everything that's below 1,000 hertz go through, you just get this kind of broad envelope of the function. Whereas if you let the high frequencies go through, you get this instead. And this may not look as recognizable, but the funny thing is that this is actually the part where the phonemes exist. I mean, you can actually filter out all the low components of this signal and still understand everything that's being said perfectly. You just won't be able to hear it from a long way away. So it's I could play you some examples. It's kind of interesting. But yeah, any further questions? And then I'll sign off. Well, I think that if you're going to go to wavelet transform, you're probably going to approach it from a different angle entirely. You're probably going to approach it more from the parametric fitting. Because the wavelet transform is going to be taking some basis function and then shearing it and then also shifting it and translating it. And so that essentially is just doing a parametric fitting for how well can this function be decomposed into this other function that I'm moving around.